We are in section 11.9, representation of functions as power series. In this section, we learn how to represent certain types of functions as sums of power series by manipulating geometric series or by differentiating and integrating series. This method is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations, and for approximating functions by polynomials. So remember that a geometric series was able to have a sum rewritten as a1 over 1 minus r. Remember that a1 was that first term and r was that common ratio. That was what we were using to multiply from term to term to term. And so if you notice down below in the box, if you were to go from a1, which is 1, and go from term to term to term, we are multiplying by an x each time. And so hopefully you can see that that is how we arrive at the f of x equals 1 over 1 minus x formula that we have. Also to note here, there is an x which is also written as our sum from n equals 0 to infinity of x to the nth power. And then to figure out where it's going to be convergent, we have the absolute value of x is less than 1. It says, note this is a geometric series with a equal to 1 and r equal to x. This is of the form we want the function to be in to find the power series representation. The interval of convergence that we have is the absolute value of x is less than 1. So the example right below says find a power series representation for the function and determine the interval of convergence. So the first problem that we have here, we note that it is really set up nicely this time. It has a 1 in the numerator, a 1 minus in the denominator, and then this time instead of an x, we have a 3x. So this 1 over 1 minus 3x can be rewritten as the sum from n equals 0 to infinity of, and that value that we have in place of our x is a 3x, so it's going to be 3x to the nth power. And this could also be rewritten as the sum from n equals 0 to infinity of 3 to the n, x to the n. And so this would be what we would have for our power series representation. And then to determine the interval of convergence, we would have the absolute value of 3x needs to be less than 1. And we know that this would be equal to the absolute value of 3 times the absolute value of x, which is less than 1. The absolute value of 3 is just 3 times the absolute value of x, which is less than 1. Or the absolute value of x would be less than 1/3. So our radius of convergence is going to be equal to 1/3. And our interval of convergence is going to go from negative 1/3 to 1/3. And we do not include those endpoints either. Part B says f of x equals 1 over 1 plus 2x. And this one we do need to manipulate a little bit. We have, this is the same thing as 1 minus negative 2x, if you were to rewrite it that way. And then from here, we would say that this is equal to the sum from n equals 0 to infinity of, and the object that we have this time is a negative 2x. So we have negative 2x raised to the nth power, or the sum from n equals 0 to infinity of negative 2 to the nth, x to the nth power, which would be our representation for the function as a power series. To figure out that radius and interval of convergence, we have the absolute value of negative 2x is less than 1, or the absolute value of negative 2 times the absolute value of x is less than 1, which works out to being 2 times the absolute value of x is less than 1, or the absolute value of x is less than 1/2, which means that our radius of convergence is 1/2, and our interval is going to be from negative 1/2 to positive 1/2. Part C also needs to be manipulated, and we can rewrite this as 1 over 1 minus negative 4x squared, just like how we did in the previous example. And so for this, we would have the sum from n equals 0 to infinity of, and this time we have a negative 4x squared. So negative 4x squared to the nth power, which would be equal to the sum from n equals 0 to infinity of negative 4 to the nth power, and then x to the 2n power. And this would be our power series representation for this function. To figure out the radius and interval of convergence, we would have the absolute value of negative 4x squared less than 1. And this would be the absolute value of negative 4, or just 4, times the absolute value of x squared is less than 1. This is also the same thing as 4 times the absolute value of x, and then squaring that, less than 1. Or we would say the absolute value of x squared is less than 1/4, or the absolute value of x is less than, and taking that square root on both sides, plus and minus with this, with the inequality, is going to be that it is less than 1/2. And so our radius of convergence is going to be equal to 1/2, and our interval of convergence is going to be from negative 1/2 to positive 1/2. Part D, right next to this one, says f of x equals 5 over 1 minus 4x squared. So very similar to what we just did. However, we do have a 5 in the numerator. And so to deal with that, we're just going to say 5 times 1 over 1 minus 4x squared. And so for our power series representation, we're going to have a 5 times sigma from n equals 0 to infinity of 4x squared to the nth power, which is the same as 5 times the sum from n equals 0 to infinity of 4 to the n x to the 2n. And this would be our power series representation that we would have. To figure out the radius and interval of convergence, we would have the absolute value of 4x squared is less than 1, or 4 times the absolute value of x then squared is less than 1, or the absolute value of x squared less than 1/4, or that the absolute value of x is less than 1/2. So again, the radius of convergence is going to be 1/2. The interval of convergence is going to go from negative 1/2 to 1/2. So there are 2 more of these on the following page, and I'm going to go ahead and circle both E and F, and we will look at those 2 together in class. Right below this, it says theorem. If the power series c sub n times x minus a to the nth power has a radius of convergence r greater than 0, then the function f defined by f of x equals c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus and so on. And this is going to be the sum from n equals 0 to infinity of c sub n times x minus a to the nth power is differentiable and therefore continuous on the interval a minus r, comma a plus r. And we have 2 things here to note. First one is going to be that f prime of x is equal to, and you'll notice that power rule. The first term is gone since that would just be a constant. And then we have c1 plus 2 times c2 x minus a plus 3 times c3 x minus a squared, and so on, which is equal to the sum from n equals 0 to infinity of n times c to the n times x minus a to the n minus 1 power, using that power rule while taking the derivative. So part 2 says the integral of f of x will equal, and c is going to be our constant, and that's a capital C, not a lowercase c, plus c0 times x minus a plus c1 times x minus a squared over 2 plus c2 times x minus a cubed over 3 plus and so on is going to be equal to that constant plus the sum from n equals 0 to infinity of c sub n times x minus a to the n plus 1 power, all divided by n plus 1. The radius of convergence and the power series in equation 1 and 2 are both going to be r. So 1 and 2 do not necessarily have the same interval of convergence. So 1 and 2 don't necessarily have same interval of convergence. So the example right below says find a power series representation for the function and determine the radius of convergence. So the function that we have is tangent inverse of x. And so for this, I cannot think of a power series representation. However, I do know that the derivative f prime of x is equal to 1 over 1 plus x squared, which looks more like that power series, which I could then rewrite as 1 over 1 minus negative x squared, which will be equal to the sum from n equals 0 to infinity of negative x squared to the nth power. Or we can rewrite this as the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n power. And so for this, we would have our radius of convergence would be the absolute value of negative x squared has to be less than 1, or that the absolute value of x would be less than 1, taking that negative 1 out and then also square rooting both sides. So our radius of convergence would be equal to 1. And so this is not the inverse tangent function that we would like to have. This was the derivative. And so to go back to tangent inverse of x, we would have to integrate this power series, this function that we have, which was 1 over 1 plus x squared dx, which would be equal to integrating the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n power dx. And so this would be the same as the integral of, and evaluating this, so substituting in n equals 0, we would have 1. Substituting in n equals 1, we get minus x squared. Substituting in n is equal to 2, we have plus, and it would be x to the 4th. The next term would be minus x to the 6th, and this continues on. And then I'll put my dx also there. So integrating this, I'm going to put my constant first, plus integrating 1, we get x, minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, and then this also continues on forever. So in order to figure out what that value of c is that we have, this constant, I'm going to let x equal 0. And if x equals 0, we have tangent inverse of 0 is equal to c plus, and then the first term would be 0 plus 0 cubed over 3 plus 0 to the 5th over 5, and I'll just put, and continuing this process on. And so this would just be 0 is equal to c plus 0, or just c is equal to 0. And so from here, we would say that tangent inverse of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on, which would be equal to the sum from n equals 0 to infinity of negative 1 to the nth power x to the 2n plus 1 divided by 2n plus 1. And this would be our power series representation for the function f of x equals tangent inverse of x. So part B says f of x equals x over 2 minus x to the 3rd power And note that this is exactly the same thing as x cubed over 2 minus x to the third power. But to figure out what to rewrite this as for my power series, I'm going to think about taking the x cubed out, and to make this look more like a power series, I'm going to take out the x cubed and have 1 over 2 minus x raised to the third power. And just consider this part that we have in the parentheses, which is 1 over 2 minus x. And dealing with this, I would have 1 over 2 minus x, which is not yet written like a power series. I have a 2 in the denominator that needs to be a 1. So I can factor out a 2, and I'd have 1 minus x over 2. You can always check this by distributing that 2 back in to make sure that that worked. So this would be equal to 1/2 times the sum of, and this time we have x over 2. So x over 2 to the nth power, which would also be the same thing as the sum of x to the nth over 2 to the nth, but you also have an additional 2 out here, so we can write 2 to the nth plus 1, since there's an extra 2 in front of the sigma. And so for this, that radius of convergence would be the absolute value of x over 2 is less than 1, or we would have the absolute value of x all over 2 is less than 1, which means that the absolute value of x is less than 2, and so r would be equal to 2. And so the issue that we have here is that I don't just have 1 over 2 minus x. It's raised to a power. It's raised to the third power. So in able to get this third power, I'm going to take a derivative. And so first thing is the derivative of 1 over 2 minus x is going to be 2 minus x times 0 minus -1 over 2 minus x squared, which equals 1 over 2 minus x squared, which is almost what we want. We want it raised to the third power, so we're close. So this means I would have to take the derivative of my power series that we have written so far, which is the sum from n equals 0 to infinity of x to the n over 2 to the n plus 1, which is going to be equal to the sum. And since we took the derivative, the first term would be gone. So we're going to say from n equals 1 to infinity of, and using the power rule, it's going to be n times x to the n minus 1 all over that constant value, which would just be 2 to the n plus 1. So we are almost at what we would like. Our denominator needs to be raised to the third power. Right now it's raised to the second. So I'm going to go ahead and take the derivative again, but this time of 1 over 2 minus x squared. And so we would have 2 minus x squared times 0. And again, this is using the quotient rule, minus the top, which is 1, times the derivative of the denominator, which is going to be 2 times 2 minus x to the first, times the derivative of the inside, which would be -1, all over 2 minus x to the fourth power. And this is going to simplify to 2 times 2 minus x all over 2 minus x to the fourth. One of the terms 2 minus x's would cancel, and we would arrive at 2 over 2 minus x to the third power. And so the derivative that we have here of the sum from n equals 1 to infinity of n times x to the n minus 1 over 2 to the n plus 1 would be equal to And since we take the derivative, we're now going to be starting our summation at 2 to infinity is going to be n times n minus 1 x to the n minus 2 power all over 2 to the n plus 1. To make our summation start at 0 again, so to change n equals 0, we need to add 2 to all n's. And so to do that, this would imply that we're going to have the sum from n equals 0 to infinity. That first term, we would add 2 to it. We're going to have n plus 2. The second term, n minus 1 plus 2, would be n plus 1. X to the nth, since we'd have n minus 2 plus 2, and then divided by 2 to the n plus 1 plus 2, or 2 to the n plus 3. So back to our original function that we had, which was x over 2 minus x to the third power, which is x cubed over 2 minus x cubed, which we said from up above is equal to x cubed times 1 over 2 minus x cubed. But we do have an issue here. The issue is going to be that there is an extra 2 in here. And so mathematically, if you have a 2 in the numerator, you can put a 2 in the denominator, and it's like nothing has been done to it mathematically. So rewriting this, again with that 2 in the numerator, 2 in the denominator, so it matches the derivative that I have up above. And this would be equal to x cubed over 2 times, and we just arrived at what this was equal to, which is stated right up above, which is going to be the sum from n equals 0 to infinity of n plus 2 times n plus 1 times x to the n all over 2 to the n plus 3. And so to rewrite this, notice that you can combine your x's together. And so it's going to be the sum from n equals 0 to infinity of n plus 2 times n plus 1 times x to the n plus 3 all over, and currently we have 2 to the n plus 3, and there's one more 2 that we're going to add in, so it's 2 to the first, so now this is going to become 2 to the n plus 4. And this would be our power series representation for this function.